Welcome to 18th lecture. We are studying basic electrical engineering. Today we'll study Norton's theorem. Before this, we have studied Thevenin's theorem. This theorem is not very different from Thevenin. It's actually a sister of Thevenin's theorem. It's very similar to Thevenin's theorem. The steps are very much like we did for Thevenin's theorem. The first step is that we remove RL, and instead of open circuiting that we did for Thevenin's theorem, we short circuit the open ends, and then through the short circuit we find I short circuit. We compute our Thevenin exactly like we did for Thevenin's theorem, and then we drop this equivalent, a current source equal to the value of ISC, the short circuit current, in parallel with our Thevenin. In Thevenin's equivalent, it was a voltage source with voltage being open circuit, and R Thevenin was in series with it. Here we have a current source in parallel with the same R Thevenin, and then RL in parallel with R Thevenin. And then finally, we find our desired quantity, voltage across load or current through load. Here is an example that we solved for Thevenin's theorem, and we computed an answer V out is equal to minus 3 volts. Today we'll solve it using Norton's theorem, and we'll try to reach to the same answer. Let's start with step number 1. Remove RL and short circuit open ends. What is the step number 1? This 4 kilo ohm load and short circuit these ends. Find ISC. To find the short circuit current through this resistor, we have multiple options. Let's try the nodal analysis option. If we apply nodal analysis, we see there are 3 branches connected to this V, and this is the ground node. The current would be assumed to be moving in all these 3 directions, moving away from the node. The node current for this branch is V minus 6 divided by the resistance 6K plus V minus 12 I minus, because the current is from the negative side, adds up these highs divided by 3K plus the current in this branch V minus 0 over 2K is equal to 0. Finding V is easy. We have 6K, the largest number, the LCM, multiplying each term by 6K will solve our problem. 6K multiplying with 6K leaves it V minus 6. This 2V is minus and minus becomes plus. Multiply with 224 plus, multiplying this by 6K leaves it 3V. So we have 3V, 2V, 5 plus 1, 6V. Plus 24 minus 6 plus 18 taken on the other side becomes minus 16. So this voltage is minus 3. But we are interested in ISC, I short circuit, which is the current through this branch. So this would be V minus 0 divided by 2K. Second step is finding ISC. V divided by 2K. Take V from here, minus 3. Minus 3 by 2K. Minus 3 by 2 milliamperes. The next step is compute R Thevenin. For that, the step is exactly the same as we did for Thevenin's theorem. have 6k in parallel with 3k plus 2k plus 6 in parallel with 3. Here's 4 kilo. Now let's go to step number 4 if we draw this equivalent. Minus 3 by 2 milliampere. The value of this source ISC. The value of this resistor is equal to our Thevenin 4 kilo ohm, and we put our load back that we removed in step number 1, 4 kilo ohm. And we are supposed to find the voltage drop across this load resistor. So to find voltage drop across this resistor, the last part, step number 5, would be this current is divided between this resistor and this resistor, since both are 4 kilo ohm. So according to current divider's rule, this should be equally divided. So IL, the current through load, would be minus 3 by 2 milli divided by 2. Half of the current flows through this 4k, the remaining half through this 4k. So minus 3 by 4 milliamperes. And we are interested in finding out V out. So now we know IL, the value of this resistor is 4k. We simply multiply them together to find V out. IL times 4k, which is minus 3 by 4 milli times 4k. So V out comes out to be minus 3/4. The same answer that we obtained when we solved this same circuit using Thevenin's theorem. In the next lecture, we will study source transformation technique. That will be the last technique that we'll study before our midterm exam.